What if you could stand at the edge of a place where the laws of physics, as we know them simply, break, a place where time doesn't just slow down, it grinds to a near halt, stretching seconds into eternities? This isn't science fiction. It's the reality of a black hole's event horizon, the point of no return where gravity becomes so overwhelming that not even light can escape. These cosmic monsters aren't just fascinating, they're the ultimate paradoxes of the universe, bending space, warping time, and challenging everything we think we know. For decades, black holes have been the ultimate cosmic mysteries, hiding secrets that push the boundaries of human understanding. But what's even more astonishing are the bizarre phenomena that happen just at their edges, 35 mind-bending puzzles that scientists are still scrambling to unravel. From particles that seemingly teleport across space to quantum information that refuses to disappear, these enigmas defy logic and ignite our deepest curiosity. Why? Because black holes aren't just celestial oddities, they're the universe's way of testing the very fabric of reality itself. So what happens when you dive into the unknown, peering beyond the veil of an event horizon? What strange forces are at play in those final moments before matter vanishes forever? The answers might rewrite physics as we know it, revealing secrets about spacetime, quantum mechanics, and perhaps even the birth of new universes. Today, we're embarking on a journey to the edge of these cosmic abysses, where the rules we rely on crumble, and where the greatest mysteries of the cosmos await. Are you ready to explore what lies just beyond the point of no return? Imagine the most massive star in the universe, a colossal furnace burning brighter than 1,000,000 suns. Now picture that star collapsing under its own weight, like a skyscraper imploding inward at unimaginable speeds. That's how a black hole is born. When a dying star exhausts its nuclear fuel, gravity wins the ultimate tug of war, crushing matter into an infinitely dense point called a singularity. Surrounding it is the event horizon, the infamous point of no return, a boundary where escape becomes impossible, not because space ends, but because the pull of gravity bends it into an inescapable trap. Think of spacetime as a trampoline. Place a bowling ball in the center, and the fabric stretches downward. That's what massive objects like stars do to the universe's fabric. Now replace that bowling ball with a needle, something infinitely tiny yet impossibly heavy. The trampoline doesn't just dip, it tears. That's a black hole's singularity, warping spacetime so severely that the rules we know cease to apply. Einstein's theory of relativity predicted these cosmic anomalies over a century ago, revealing how gravity isn't just a force but the bending of spacetime itself. Yet when quantum mechanics enters the picture, things get messy. At the edge of a black hole, the orderly predictions of relativity clash with the chaotic uncertainty of quantum particles, creating paradoxes that leave even the brightest minds stumped. But here's where it gets stranger. Black holes aren't just cosmic vacuum cleaners sucking everything in forever. They leak, they glow. They might even hold the key to understanding how information, the very blueprint of reality, persists in a universe where nothing escapes. And that's just the beginning of the enigmas lurking at their edges. Picture an astronaut drifting toward a black hole, feet first. At first, nothing seems unusual, just the vast emptiness of space. But as they near the event horizon, something unimaginable happens. Their body begins to stretch, as if an invisible hand is pulling them apart like warm taffy. Their legs stretch thinner and thinner, elongating toward the black hole while their upper body resists slightly less. Within moments, they're no longer a person but a grotesque, noodle-like strand, a process scientists call spaghettification. This isn't some gruesome sci-fi scenario. It's the brutal reality of tidal forces, where gravity's pull is so intense and uneven that it overcomes the molecular bonds holding matter together. Here's why: the force of gravity isn't uniform, it's stronger on the side of an object closer to the black hole. Imagine holding a rubber band between your hands and pulling one end harder than the other. The stretch becomes uneven, just like our doomed astronaut. The difference in gravity between their head and toes, what physicists call the tidal force, literally rips them apart long before they cross the event horizon. Renowned astrophysicist Neil deGrasse Tyson once described this as cosmic taffy, where the black hole's gravity plays the role of an unforgiving candy machine. But here's the twist: not everything gets stretched into oblivion. Smaller, sturdier objects like a chunk of neutron star material or a dense robotic probe might survive longer thanks to their rigid structure. Even stranger, some theoretical models suggest certain black holes rotate so fast that their tidal forces weaken near the edges, offering a slim chance for objects to slip through relatively unscathed. So why does this matter? Because spaghettification isn't just a cosmic horror show. It's a clue. The way matter behaves at the edge of a black hole reveals secrets about gravity's extremes, testing whether Einstein's equations hold up or if new physics takes over. And if we ever observe an object defying this fate, that could rewrite the rules entirely. If you've ever watched the movie Interstellar, you might remember the scene where astronauts on a planet near a black hole experience time so differently that hours for them become decades for everyone else. That wasn't just Hollywood magic, it was real science. Black holes don't just bend space, they twist time itself into a surreal slow-motion spectacle. This mind-bending effect is called time dilation, and it's one of the most astonishing consequences of Einstein's theory of relativity. Here's how it works. The closer you get to a black hole's immense gravitational pull, the more space-time warps, making time crawl compared to someone far away. Imagine two clocks, one placed near a black hole's edge, the other floating safely in distant space. The clock near the black hole would tick slower, as if trapped in cosmic molasses. This isn't just theoretical. Even here on Earth, GPS satellites orbiting high above us have to account for tiny time distortions caused by our planet's gravity. If they didn't adjust for it, your phone's navigation would be off by miles within minutes. But near a black hole, the effect is extreme. If you could hover just outside the event horizon and peer inward, you'd witness something bizarre. A person falling in would appear to move in ultra-slow motion, their final moments stretched into what looks like an eternity. Their image would fade to red as light struggles to escape the black hole's pull, a phenomenon called gravitational redshift. And then nothing. From your perspective, they'd never quite cross the horizon, frozen in time like a cosmic still frame. Yet for them, time would feel normal, and the plunge would happen in seconds. This raises a haunting question. If time grinds to a halt at the edge from an outsider's view, does anything ever truly fall in? Some theories suggest the black hole's surface might be littered with these ghostly, time-frozen remnants, a cosmic museum of everything that ever approached. Others argue quantum effects blur this paradox, meaning reality might be far stranger than we can imagine. Time dilation isn't just a curiosity, it's a gateway to understanding how gravity and time intertwine, reshaping our view of the universe's most fundamental fabric. And if that twists your brain, just wait, because the next paradox dives even deeper into the quantum chaos lurking at the edge. Standing at the edge of a black hole, you'd witness something that defies common sense. A falling object doesn't vanish, it freezes. Not in the literal sense, but from your perspective, the object's final moments stretch into an infinite tableau, hovering just outside the event horizon like a cosmic still life. This eerie illusion, once dubbed the frozen star paradox, reveals how black holes manipulate not just space, but our very perception of reality. Here's the science behind the mirage. As an object approaches the event horizon, the light it emits fights against the black hole's gravitational grip. Photons, particles of light, lose energy as they climb out, shifting to longer, redder wavelengths in a process called gravitational redshift. The closer the object gets, the more extreme this shift becomes. Eventually, the light becomes so faint and stretched that it's practically undetectable, creating the illusion that the object has stopped in time. The final visible photon lingers at the horizon, imprinting a ghostly afterimage that fades over eons. Early physicists like Einstein and Oppenheimer wrestled with this paradox, theorizing that black holes might be frozen stars, collapsed objects eternally suspended at their own event horizons. But modern astronomy paints a wilder picture. The freezing effect is just a trick of perspective. To an outside observer, time slows to a crawl near the horizon, but for the falling object, it plunges through in an instant, torn apart by tidal forces or vanishing into the singularity. Yet this illusion hints at something profound. Black holes aren't the perfect voids we once imagined. Thanks to quantum mechanics, they glow. In the 1970s, Stephen Hawking discovered that black holes slowly leak radiation, a faint whisper of energy now called Hawking radiation. Virtual particles constantly popping in and out of existence near the horizon can get separated. One falls in, the other escapes, stealing a tiny bit of the black hole's mass. Over trillions of years, this process could evaporate a black hole entirely, leaving behind only a burst of radiation as its final signature. So why does this matter? Because the frozen star illusion and Hawking radiation reveal a cosmic tug-of-war between gravity and quantum physics. The event horizon isn't just a boundary, it's a laboratory for the universe's deepest laws, where light bends, time warps, and particles cheat death. And if we can decode these paradoxes, we might just unlock the secrets of spacetime itself. Stephen Hawking turned our understanding of black holes upside down when he made a jaw-dropping prediction. These cosmic vacuums aren't completely black. They glow not with the fiery light of stars, but with a faint, ghostly radiation that slowly chips away at their mass. This phenomenon, now called Hawking radiation, reveals something startling. Black holes aren't eternal. Given enough time, trillions upon trillions of years, they can evaporate into nothingness. But how does light escape the universe's ultimate prison? The answer lies in the bizarre world of quantum mechanics, where particles cheat death in ways that defy common sense. Picture empty space near a black hole's event horizon. It's not actually empty. At the quantum level, pairs of virtual particles constantly pop in and out of existence, borrowing energy from the universe before annihilating each other in a fleeting instant. Normally, these particles vanish without a trace, but near a black hole's edge, gravity plays a cosmic trick. One particle gets sucked in while the other escapes, stealing a tiny bit of the black hole's energy in the process. The escaping particle becomes real radiation, Hawking radiation, while its doomed partner adds negative energy to the black hole, shrinking it ever so slightly. This isn't just theoretical. In 2014, scientists created an artificial event horizon in a lab using sound waves, observing particle behavior eerily similar to Hawking's predictions. But here's where things get messy. According to quantum mechanics, information, the fundamental blueprint of particles, can never be destroyed. Yet if a black hole evaporates, what happens to all the information swallowed by its singularity? Does it vanish forever, violating the laws of physics? This is the infamous black hole information paradox. a puzzle so profound it sparked decades of debate among physicists. Some theories suggest the information gets scrambled and encoded in Hawking radiation, leaking out in a garbled cosmic whisper. Others propose it's trapped in a remnant or even ejected into a parallel universe. If Hawking was right, then black holes aren't just devourers of matter. They're cosmic recyclers, transforming everything they consume into something entirely new. And if we can crack this paradox, we might finally bridge the gap between Einstein's gravity and the quantum realm, rewriting the laws of physics as we know them. One of the most unsettling mysteries at the edge of a black hole isn't about what gets pulled in. It's about what happens to the information carried by that matter. According to quantum mechanics, information, the fundamental details that make up particles and their states, can never truly vanish. It might get scrambled or hidden, but the universe keeps perfect records. Yet black holes seem to break this rule. When matter crosses the event horizon, dragging its information into the abyss, does it disappear forever? This is the black hole information paradox, a cosmic tug of war between gravity and quantum theory that's kept physicists awake for decades. Think of it like burning a book. The pages turn to ash, but in theory, if you could track every molecule of smoke and heat, you could reconstruct the original text. Quantum mechanics says the universe works the same way. Information is always preserved, just transformed. But toss that book into a black hole, and the rules seem to collapse. The singularity doesn't just scramble the information, it potentially erases it from existence. That's like burning the book and having the ashes vanish into thin air, a violation of quantum law so severe it threatens our understanding of reality. Enter the firewall paradox, a radical idea suggesting the event horizon might be a searing wall of energy that incinerates anything crossing it. Proposed in 2012, this theory argues that to preserve quantum rules, black holes must destroy information at the horizon rather than let it fall in. But this creates another problem. Einstein's relativity insists that crossing the event horizon should feel like nothing special, no fireworks, no sudden burns. You'd only notice the tidal forces pulling you apart. So which is it, a peaceful plunge or a violent cosmic barbecue? The debate rages on, with some physicists arguing firewalls are unnecessary, while others see them as the only way to resolve the paradox. But here's where it gets wild. Black holes might not delete information after all. They could be hiding it in plain sight. One theory suggests that information isn't lost inside the black hole, but smeared across its event horizon, encoded in tiny, pixel-like patches called holographic bits. Just like a two-dimensional hologram can project a 3D image, the surface of a black hole might hold all the information about what fell inside, like a cosmic thumb drive. Another mind-bending idea: the information leaks out via Hawking radiation, scrambled but recoverable, like a book shredded into confetti, but with each piece carrying a fragment of the original text. If we crack this puzzle, it won't just solve a black hole mystery, it could rewrite physics. The information paradox forces us to ask, is space-time itself a hologram? Are black holes the universe's ultimate encryption devices? Every answer leads to deeper questions, proving that at the edge of these cosmic voids, the universe keeps its most profound secrets waiting to be uncovered. What if everything you see, touch, and experience, the vast three-dimensional universe with its galaxies, stars, and planets, was actually just a projection, like an elaborate cosmic hologram? It sounds like science fiction, but this mind-bending idea, known as the holographic principle, emerges from the strange physics at the edge of black holes. The theory suggests that all the information contained within a black hole's three-dimensional volume might be perfectly encoded on its two-dimensional event horizon, like a DVD storing an entire movie on its flat surface. Even wilder, some physicists argue this might not just apply to black holes. Our entire universe could be a holographic projection, with reality as we know it unfolding on some distant, unseen boundary. This radical concept traces back to the 1990s, when physicist Gerard T. Hooft and later Leonard Susskind proposed that black holes don't destroy information, but instead store it in tiny, pixel-like patches on their surfaces. Imagine taking all the data describing every atom, photon, and quark that ever fell into a black hole and compressing it into a vast, ultra-high-resolution image painted onto the horizon. That's the essence of the holographic principle, a cosmic data compression scheme so efficient it flattens reality itself. But how does this connect to the universe at large? Enter string theories add S/CFT correspondence, a groundbreaking idea suggesting a black hole's two-dimensional boundary and its three-dimensional interior are mathematically equivalent. In simpler terms, the physics playing out on the surface like a flat, abstract screen perfectly mirrors the chaotic, curved spacetime inside. It's as if the black hole is running a cosmic simulation, with the event horizon acting as the processor and the interior as the rendered output. This raises a staggering question. If black holes can encode 3D information on 2D surfaces, could our universe be doing the same? Some theories propose that the entire cosmos might be a hologram with the fabric of reality projected from a hidden, lower-dimensional boundary we can't perceive. Think of it like a video game. What you see on your screen is a 3D world, but it's all generated by 2D code running behind the scenes. If true, it would mean everything from supernovas to the neurons firing in your brain is just a shadow of a deeper, flatter reality. Black holes might even be nature's most powerful computers, performing calculations at their horizons that manifest as the physics we observe. Every particle falling in could be like a line of code, processed and transformed into the holographic data that defines spacetime itself. If we ever crack how this cosmic computation works, it could reveal whether we're living in a simulated universe or something far stranger. The holographic principle doesn't just challenge our understanding of black holes, it forces us to rethink the very nature of existence. And if that doesn't make your head spin, just wait, because the next phenomenon dives even deeper into the quantum chaos lurking at the edge. Black holes were once thought to be the simplest objects in the universe, featureless voids defined only by their mass, spin, and charge. But in the early 1970s, a young physicist named Jacob Bekenstein dropped a bombshell. These cosmic monsters aren't just simple pits of gravity. They have entropy, a measure of disorder that had physicists reeling. Why? Because entropy is a property of complex systems with countless microscopic states. Think of a messy room with clothes strewn everywhere or gas molecules chaotically bouncing around. How could a black hole, seemingly just empty spacetime curved to infinity, behave like a boiling pot of particles? The answer lies in the event horizon's surface area. Bekenstein and later Stephen Hawking discovered something revolutionary. A black hole's entropy isn't proportional to its volume but to the area of its event horizon. The more massive the black hole, the larger its surface and the more entropy it contains. This became the Bekenstein-Hawking formula, a cornerstone of black hole thermodynamics. But what does that actually mean? Imagine taking all the information about every particle that ever fell into the black hole, every star, planet, or speck of dust, and smearing it across the horizon like cosmic graffiti. The entropy tells us how many hidden ways that information could be arranged, like invisible puzzle pieces we can't quite see. This revelation was staggering because it hinted at something profound. Black holes aren't just empty pits. They have structure. Their event horizons might be buzzing with microscopic degrees of freedom, tiny, invisible pixels storing information in ways we don't yet understand. Think of it like a hard drive. From the outside, it looks smooth and simple, but inside, it's packed with data encoded in microscopic bits. Black holes might work the same way, with their entropy acting like a cosmic ledger keeping track of everything they've consumed. The implications go even deeper. In ordinary thermodynamics, entropy always increases. A cup shatters, ice melts, systems trend toward chaos. Black holes obey this rule too. When they merge, their combined horizon area is always larger than the sum of their parts, meaning their total entropy grows. This fits perfectly with the second law of thermodynamics, but it raises a bizarre question. If black holes have entropy, they must also have temperature. And if they have temperature, they must emit radiation. That's how Hawking was led to his groundbreaking prediction of black hole evaporation, a discovery that tied gravity, quantum mechanics, and thermodynamics together in ways no one expected. So what's really going on at the horizon? Some theories suggest it's a seething quantum foam, where spacetime itself churns with virtual particles popping in and out of existence. Others propose it's a holographic screen, encoding the black hole's entire history in 2 dimensions. Whatever the answer, one thing is clear: black holes are anything but simple. Their entropy is a cosmic clue, pointing us toward a hidden layer of reality where gravity and quantum mechanics collide, and where the universe's deepest secrets might be written in the language of disorder. At the heart of every black hole lies its greatest mystery, the singularity. This is the point where all the stars' collapsed mass is crushed into an infinitely dense, infinitely small speck. But here's the problem: infinity isn't a real physical quantity. It's a mathematical warning sign, screaming that our equations have broken down. According to Einstein's general relativity, gravity at the singularity becomes so strong that spacetime itself curves to an infinite degree, rendering all known physics meaningless. It's like dividing by zero, a calculation that spits out nonsense because the rules we rely on don't apply anymore. This isn't just a theoretical headache, it's a crisis for modern physics. The singularity suggests that somewhere beneath the event horizon, the universe stops playing by any rules we understand, but nature abhors infinities. Quantum mechanics, which governs the tiny world of particles, might hold the key to fixing this cosmic glitch. Unlike relativity, quantum theory deals in discrete packets, tiny grains of space, time, and energy. If we combine these 2 frameworks into a theory of quantum gravity, the singularity might not be infinitely dense after all. Instead, it could be a fuzzy, roiling knot of spacetime where quantum effects take over, preventing the infinite collapse relativity predicts. One leading candidate, loop quantum gravity, proposes something even wilder. Black holes might not end in singularities at all. Instead, the crushing gravity could trigger a quantum bounce, where spacetime recoils like a compressed spring. In this scenario, the black hole's core wouldn't be a dead end, it could be a tunnel to somewhere else. Picture a rubber band stretched to its limit. Just before it snaps, quantum physics might step in, flipping the collapse into an expansion. Some theories even suggest this could birth a new universe inside the black hole, or spit matter out through a white hole, a hypothetical cosmic exit where everything that falls in here comes rushing out elsewhere. That's where wormholes enter the conversation. If singularities are replaced by quantum bridges, could black holes be secret passageways through spacetime? Einstein's equations do allow for such tunnels, called Einstein-Rosen bridges, but they'd normally snap shut instantly under their own gravity. However, with quantum effects in play, these wormholes might stay open long enough to connect distant regions of space or even different universes. Of course, any traveler daring to enter would still face tidal forces fierce enough to shred atoms, but mathematically, the possibility remains tantalizing. The singularity isn't just a failure of physics, it's an invitation to discover what lies beyond relativity, beyond quantum mechanics, perhaps beyond space-time itself. Solving this riddle won't just rewrite textbooks, it could reveal whether black holes are cosmic endpoints, gateways, or something even stranger. One thing's certain, where our math breaks down, reality is hiding its greatest secrets. What if black holes weren't just cosmic dead ends but secret passageways? The idea of wormholes, those hypothetical tunnels through space-time, has long fascinated scientists and sci-fi fans alike. Remember the iconic scene in Contact, where Jodie Foster's character plunges through a shimmering vortex, hurtling across the universe in moments. That cinematic vision isn't pure fantasy. Wormholes are mathematically possible under Einstein's theory of relativity, but there's a catch. These cosmic shortcuts would need something bizarre to stay open: exotic matter. Exotic matter isn't your everyday atoms. It's a hypothetical substance with negative energy, capable of repelling gravity rather than attracting it. Picture a tunnel collapsing under its own weight. Exotic matter would act like an invisible force field, propping it open against the crushing pull of space-time. Without it, any wormhole would snap shut faster than you could blink, trapping anything inside. The problem: we've never observed exotic matter in nature. It exists only as a speculative solution in equations, leaving wormholes in the realm of what if for now. But here's where black holes enter the equation. Some theories suggest that deep inside a black hole's singularity, the laws of physics might twist space-time so violently that it punches a hole into another region of the universe, or even another universe entirely. This isn't just a wild guess. Equations in loop quantum gravity, a leading theory attempting to unite relativity and quantum mechanics, hint that black holes could transform into white holes, theoretical cosmic exits where matter bursts outward instead of vanishing inward. Imagine a black hole's singularity rebounding like a compressed spring, spewing out everything it once swallowed. This raises a mind-bending possibility. Black holes might not destroy. They could create. Some cosmologists, like Nobel laureate Roger Penrose, propose that our own universe might have been born this way, a white hole erupting from a black hole in some parent cosmos. If true, every black hole could be a potential Big Bang in disguise, birthing new universes with their own laws of physics. It's a cosmic Russian nesting doll where universes spawn inside one another, forever hidden behind event horizons. Wormholes and white holes remain speculative, but they push us to ask bigger questions. Are black holes the universe's recycling centers? Could they be bridges to other realities? Until we crack quantum gravity, these ideas live at the edge of science where imagination and equations collide, and where the universe's strangest secrets might be hiding. Could our universe be the offspring of a black hole from another cosmos? Theoretical physicist Lee Smolin proposed a radical idea called cosmological natural selection, a theory so audacious it suggests black holes might be cosmic reproductive organs, birthing entirely new universes with slightly altered physics. Think of it like biological evolution, but on a galactic scale. Just as random mutations drive diversity in life, Smolin argued that each new universe spawned inside a black hole could have tiny variations in its fundamental constant, like the strength of gravity or the mass of electrons. Over cosmic time, universes that produce more black holes would reproduce more often, leading to a multiverse where the laws of physics favor black hole formation. It's Darwinism applied to the cosmos itself. This isn't just wild speculation. Smolin's theory tackles a haunting question: why do the constants of nature seem fine-tuned for life? If universes evolve, the ones that survive and multiply would inevitably develop conditions ripe for black holes, and by extension, the building blocks of stars, planets, and even us. It's a cosmic twist on the anthropic principle, where the universe isn't designed for life, but life emerges because the universe is optimized for black holes. But here's the real kicker. If black holes can create universes, could our own universe have been born this way? Some theories suggest the Big Bang might have been the explosive rebound of a singularity in a parent universe, a white hole erupting from a black hole's collapse. Imagine our entire cosmos as a bubble inflating inside some greater, unknowable reality. The math even allows for it. The infinite density of a singularity could have pinched off into a new spacetime continuum, complete with its own laws of physics. So how would we test this? Look for anomalies. If our universe inherited genetic tweaks from its parent, there might be subtle fingerprints in the cosmic microwave background, the afterglow of the Big Bang. Or perhaps the distribution of black holes in our cosmos holds clues, revealing patterns that hint at a deeper evolutionary process. Black hole cosmology blurs the line between physics and philosophy, forcing us to ask, are we just one link in an endless chain of cosmic reproduction? And if so, what does that say about the very fabric of reality? The answers might lie not in the stars, but in the abyss. Imagine a cosmic lighthouse so bright it outshines an entire galaxy, a single point of light blazing with the energy of 1 trillion suns. That's a quasar, the universe's most luminous phenomenon, and at its heart lies a supermassive black hole gone wild. But how does something known for devouring light become the brightest object in existence? The answer lies in the chaos of its accretion disk, a swirling vortex of gas, dust, and doomed stars spiraling toward oblivion at nearly the speed of light. As matter falls toward the black hole, friction heats it to millions of degrees, turning the disk into a ferocious inferno. This isn't just random chaos, it's a cosmic engine of unimaginable power. The disk glows so intensely that it can outshine every star in its host galaxy combined, lighting up the cosmos like a beacon visible across billions of light years. But the real spectacle happens at the poles, where the black hole's magnetic fields coil into cosmic particle accelerators, firing jets of superheated plasma at near light speed. These relativistic jets stretch for thousands of light years, punching through galaxies like celestial blowtorches. Quasars aren't just flashy cosmic anomalies, they're galactic architects. In the early universe, their jets sculpted the first galaxies, heating surrounding gas and regulating star formation. Some theories suggest they even seeded the cosmos with heavy elements, spreading the building blocks of planets and life. But today, most quasars have gone silent. Their black holes still lurk in galactic centers, but without enough fuel to ignite their brilliance. Our own Milky Way's supermassive black hole, Sagittarius A, is a quiet neighbor by comparison, a sleeping giant that occasionally snacks on a passing star. The difference between a quasar and a dormant black hole boils down to one thing: a cosmic buffet. When galaxies collide or gas clouds wander too close, the feast reignites the engine, proving that even the darkest voids can become the universe's brightest torches if given the chance. Not all supermassive black holes blaze like quasars. Some lurk silently in galactic centers, invisible except for the subtle dance of stars trapped in their gravitational grip. Take Sagittarius A, the dark giant at the heart of our Milky Way, 4 million times the mass of our Sun, yet so dormant it emits less energy than a handful of stars. How do we even know it's there? Because the stars around it tell a story written in motion. For decades, astronomers tracked the orbits of stars near our galaxy's core, watching as they whipped around an unseen point at speeds exceeding 3 million miles per hour. One star, called S2, completes its elliptical orbit every 16 years, coming perilously close to the black hole's edge, close enough that Einstein's predicted time dilation subtly slows its light. These stellar trajectories reveal Sagittarius A's presence more clearly than any telescope could, like detectives mapping a hidden predator by the disturbed paths of fleeing prey. The eerie quiet of these dark giants raises a deeper question. Why are some supermassive black holes dormant while others shine as quasars? The answer lies in their cosmic diet. Quasars feast on torrents of gas and stars, their accretion disks glowing with the heat of a trillion suns. But Sagittarius sits in a relative desert with only occasional snacks, like the gas cloud G2, which passed too close in 2014 and was stretched into a cosmic noodle before vanishing silently. Without a steady flow of matter, the black hole's engine idles, its terrifying power hidden beneath the calm, yet their silence makes them no less mysterious. How did these monsters grow so massive so quickly? Some could be ancient remnants of the first stars, collapsing directly into black holes in the early universe. Others might have ballooned by merging with smaller black holes during galactic collisions, a process we've detected through gravitational waves. But the biggest puzzle: supermassive black holes existed when the universe was less than 1 billion years old, too young by conventional models to have grown so large. Their very existence challenges our understanding of cosmic evolution, hinting at formation processes we've yet to imagine. These dark giants remind us that black holes aren't just destructive forces, they're galactic anchors, shaping the evolution of the very galaxies they hide within. And somewhere between the blazing quasars and the silent titans like Sagittarius A, the universe holds clues to how these enigmatic beasts are born, live, and shape the cosmos around them. For decades, black holes seem to come in just two sizes: stellar mass black holes, the remains of collapsed stars weighing a few times our sun's mass, and supermassive black holes, the behemoths lurking in galactic centers with millions or billions of solar masses. But what about the middle children, the cosmic missing link between these extremes? Intermediate mass black holes, or IMB, have long eluded detection, leaving a glaring gap in our understanding of how black holes grow. These mysterious middleweights, thought to range from hundreds to hundreds of thousands of solar masses, could hold the key to one of astrophysics' biggest puzzles: how tiny stellar remnants balloon into the monsters that anchor galaxies. The hunt for these elusive objects has been a cosmic game of hide and seek. Unlike their supermassive cousins, IMB don't sit in bright galactic cores, and they're too hefty to form from a single collapsing star. So where do they hide? Clues have surfaced in dense star clusters where runaway collisions could forge them, or in the aftermath of ancient galaxy mergers where smaller black holes might have combined like cosmic Lego blocks. In 2020, the LIGO and Virgo gravitational wave detectors picked up a tantalizing signal: a black hole merger where the final product weighed a staggering 142 solar masses, right in the IMB sweet spot. Dubbed GW 1900-521, this event became the strongest evidence yet that middleweights exist, forged in the violent collisions of their smaller siblings. But here's where the mystery deepens. If IMB are out there, why are they so shy? One theory suggests they're cosmic wallflowers, lurking in the outskirts of galaxies where their gravitational influence is harder to spot. Others propose they're disguised by thick clouds of gas or hidden in globular clusters, their faint X-ray whispers drowned out by brighter stellar noise. Yet finding them isn't just academic. It's crucial to understanding black hole evolution. If supermassive black holes grew by feasting on IMB, these missing links could reveal how galaxies themselves assemble over cosmic time. Now imagine if black holes could sing. Gravitational waves, the ripples in spacetime from black hole mergers, aren't just signals, they're cosmic sound waves. When LIGO detects a collision, scientists convert these ripples into audible chirps, revealing the music of spacetime itself. The pitch and tempo of these chirps tell a story. Lighter black holes produce higher frequency waves like a piccolo, while mergers involving IMB would resonate with the deep, thundering tones of a tuba. Future detectors like the space-based LISA mission could soon tune into this symphony at lower frequencies, potentially uncovering IMB dancing in the cosmic shadows. The search for these middleweights isn't just about filling a gap in a catalog, it's about decoding the universe's growth chart. Every new detection peels back another layer, revealing how black holes grow, merge, and shape the cosmos around them. And if we're lucky, the next gravitational wave signal might just be the deep, resonant note we've been waiting for, the unmistakable voice of the universe's missing link. Einstein predicted them a century ago, but it took until 2015 for humanity to finally hear the universe's hidden soundtrack, gravitational waves. These ripples in spacetime, born from the most violent collisions in the cosmos, are black holes' way of singing. When two black holes spiral toward each other, locked in a deadly dance, they churn spacetime like a spoon stirring honey, sending waves radiating outward at light speed. By the time these waves reach Earth, they're vanishingly faint, stretching and squeezing our planet by less than the width of an atomic nucleus. Yet thanks to the Laser Interferometer Gravitational Wave Observatory, or LIGO, we can now eavesdrop on these cosmic symphonies. The sound is haunting, a rapid chirp that climbs in pitch before abruptly cutting off. That's the signature of black holes merging, their final orbits accelerating as they close in, culminating in a space-time shattering collision. The pitch reveals their masses, while the duration hints at how far away they are. But the real magic lies in the subtleties. By analyzing these chirps, scientists can decipher the black hole's spins, whether they're twirling in unison like synchronized dancers or clashing in a chaotic tumble. Some spin so fast they're near the cosmic speed limit, dragging spacetime around them like a whirlpool. Others barely rotate at all, suggesting they formed differently, perhaps from the quiet collapse of a massive star or the ancient mergers of smaller black holes in the early universe. These gravitational wave detections aren't just about the present, they're time machines. The black holes LIGO has spotted merged hundreds of millions or even billions of years ago, their waves only now reaching us. Some could be relics from the universe's youth, when galaxies were smaller and collisions more frequent. Others might be hierarchical mergers, black holes formed from previous mergers, growing heavier with each cosmic smash-up. Imagine a snowball rolling downhill, gathering mass until it becomes an avalanche. That's how some black holes could have ballooned into the supermassive giants we see today. But here's the twist, not all black hole duets sound the same. Some chirps are clean, like a pure musical note, suggesting the black holes merged in empty space. Others are garbled, as if the collision happened inside a dense cloud of gas or near a supermassive black hole's turbulent disk. These messy mergers could be happening in the chaotic hearts of galaxies, where black holes get trapped in cosmic traffic jams, forced together by gravity's relentless pull. Gravitational waves are more than just cosmic noise, they're a new language. One that's revealing secrets about black holes we could never see with light alone. And as detectors grow more sensitive, we'll hear even fainter whispers, perhaps catching the birth cries of primordial black holes from the dawn of time, or the faint hum of intermediate mass black holes finally stepping into the spotlight. The universe is talking, and for the first time we're listening. What if some black holes weren't born from dying stars, but are ancient relics from the very birth of the universe itself? These hypothetical time capsules, known as primordial black holes, could have formed in the first chaotic seconds after the Big Bang, when the cosmos was a seething, dense soup of matter and energy. Unlike their stellar counterparts, these black holes could be as tiny as a pinhead or as massive as a planet packed into unimaginably small spaces, lurking unseen in the cosmic shadows. And here's the wildest part: they might be hiding in plain sight, masquerading as the elusive dark matter that holds galaxies together. The idea isn't new. Back in the 1970s, Stephen Hawking and physicist Bernard Carr explored the possibility that the infant universe's extreme pressures could have birthed black holes spontaneously. Picture the cosmos as a bubbling pot of water. Regions of intense density could have collapsed under their own gravity, pinching off into microscopic black holes before stars even existed. Some might have evaporated instantly due to Hawking radiation, while others with enough mass could have survived for billions of years, drifting through space like invisible ghosts. Hawking himself famously placed bets on their existence, even suggesting they could solve one of astronomy's biggest puzzles: the nature of dark matter. If primordial black holes are abundant enough, their collective gravity might explain why galaxies rotate faster than visible matter can account for. But finding them is like searching for cosmic needles in a universe-sized haystack. Unlike black holes from dead stars, these relics wouldn't orbit companions or devour gas, making them nearly undetectable unless they pass in front of a distant star, bending its light like a magnifying glass in a fleeting phenomenon called microlensing. Yet the most explosive possibility lies in their demise. The tiniest primordial black holes, weighing less than a mountain, could be evaporating right now, ending their lives not with a whimper but a bang. Hawking predicted that as these objects lose mass, their radiation emission would skyrocket, culminating in a final gamma ray burst brighter than a supernova. Some scientists have even speculated that mysterious deep space flashes, like fast radio bursts or certain high-energy cosmic rays, could be the death cries of these ancient black holes. If they exist, primordial black holes would rewrite cosmic history, offering a living record of the universe's first moments. They could be the missing link between the Big Bang's chaos and the structured cosmos we see today, hidden architects of the dark universe, silently shaping everything from the shadows. And if we ever catch one in the act of vanishing, that flash could illuminate secrets about quantum gravity, extra dimensions, or even the birth of new universes. The hunt isn't just about finding black holes, it's about uncovering the universe's oldest fossils, buried in time itself. Crossing the event horizon should be uneventful, at least according to Einstein. His equations say you'd glide smoothly past the point of no return, blissfully unaware of your impending doom. But quantum physics paints a far more violent picture. What if the boundary of a black hole isn't just a silent threshold, but a blazing inferno? This is the Firewall paradox, a cosmic clash between relativity and quantum mechanics that threatens to rewrite our understanding of black holes. The idea erupted in 2012 when physicists Almary, Marolf, Polchinski, and Sully proposed a radical solution to the information paradox. If information can't be destroyed and black holes evaporate via Hawking radiation, then something drastic must happen at the horizon to preserve quantum rules. Their answer: a searing wall of high-energy particles, a firewall that incinerates anything crossing it. Picture stepping not into darkness, but into a cosmic furnace hotter than the core of a supernova. The firewall would scramble an object's information and encode it into Hawking radiation, satisfying quantum mechanics. But here's the catch: Einstein's relativity insists the event horizon should feel like empty space. There's no no warning sign, no sudden blaze. You'd only notice the tidal forces pulling you apart. So which is it? A peaceful descent or a quantum execution? Critics argue firewalls violate the equivalence principle, a cornerstone of general relativity, stating that free-falling observers shouldn't detect extreme forces. It's like arguing whether a skydiver in a vacuum should feel wind relativity says no, but quantum mechanics might say yes. Some theorists propose compromises, like fuzzballs, a string theory concept where black holes aren't empty pits but tangled knots of vibrating strings extending to their horizons. In this view, the entire interior is a fuzzy quantum mess, eliminating the need for a sharp firewall. Others suggest the paradox stems from treating Hawking radiation as purely thermal noise, when it might carry subtle quantum correlations that preserve information without fiery drama. The debate rages because it's not just about black holes, it's about the fabric of reality. If firewalls exist, space-time might be pixelated at the smallest scales, like a digital screen hiding its code. If they don't, we'll need another way to reconcile quantum mechanics with gravity. Either way, the paradox forces us to confront a startling truth. At the edge of a black hole, the universe might not play by the rules we know. And that uncertainty is where the next revolution in physics could be hiding. String theory offers a radical alternative to the fiery paradoxes at a black hole's edge, a concept so bizarre it reimagines these cosmic giants from the ground up. Instead of an empty void with a singularity at its core, black holes might be fuzzballs, dense tangles of vibrating strings that stretch all the way to their surfaces. Picture a ball of yarn magnified to cosmic scales, its threads writhing with energy, packed so tightly that they blur the line between matter and space-time itself. This isn't just a tweak to Einstein's vision, it's a complete overhaul, one that could solve the information paradox without resorting to firewalls or hidden holograms. The fuzzball idea stems from string theory's claim that everything in the universe, from photons to black holes, is made of tiny, vibrating strings. In traditional black hole models, the event horizon hides a singularity, a point where physics breaks down. But fuzzballs erase that problem entirely. There's no singularity, no infinite density. Instead, the entire black hole is a knot of strings, its mass and energy spread throughout its volume like a densely woven tapestry. The horizon isn't a silent boundary. It's a buzzing quantum froth where information isn't lost but stored in the string's intricate vibrations. This flips the script on the infamous no-hair theorem, which states black holes can only be defined by mass, spin, and charge like celestial bald heads with no other distinguishing features. Fuzzballs, by contrast, are anything but bald. Their strings can vibrate in countless unique ways, encoding information about everything they've ever swallowed. Imagine dumping a library into a black hole. In the old model, the books would vanish into the singularity, their information erased. In the fuzzball model, every word, every letter would be imprinted into the string's dance, preserved forever in their quantum knots. The implications are staggering. If black holes are fuzzballs, there's no need for a firewall to scramble information at the horizon. The strings handle it naturally. No more paradoxes about burning astronauts or vanishing data. But here's the catch, proving it. Fuzzballs would look nearly identical to classic black holes from afar, their differences only visible at scales smaller than an atom. Detecting those subtle signatures would require technology beyond anything we have today, like quantum gravity sensors or precision measurements of black hole ringing after mergers. Yet the math holds tantalizing promise. Fuzzballs could explain why black holes have entropy. Their stringy interiors offer trillions of ways to arrange their energy, like a cosmic hard drive with endless storage. They might even hint at a deeper truth, that spacetime itself emerges from these vibrating strings, a holographic illusion woven by the universe's smallest threads. Whether fuzzballs are real or not, they remind us that black holes aren't just puzzles, they're portals to a new understanding of reality, where the answers might lie not in the void but in the vibrations. For decades, black holes were thought to be the simplest objects in the universe, defined only by their mass, spin, and charge. The no-hair theorem, a cornerstone of general relativity, claimed these cosmic giants couldn't have any other distinguishing features. No frills, no textures, just smooth, featureless voids. But what if black holes aren't bald after all? What if they're hiding a secret layer of complexity, a kind of quantum hair that whispers clues about their past? Recent breakthroughs have turned this idea on its head. Advanced simulations and theoretical work suggest black holes might carry subtle imprints of quantum fields, invisible structures lingering just outside their event horizons. Imagine running your fingers through wet hair and leaving behind a faint pattern. Similarly, as matter falls into a black hole, quantum fields like the electromagnetic field or even hypothetical dark matter fields could leave behind delicate traces. These aren't literal strands, of course, but fluctuations in the fabric of spacetime itself, encoding information about what the black hole has consumed. The implications are staggering. If black holes have hair, it could solve the information paradox by preserving details of swallowed matter in these quantum fingerprints. Some models even suggest these fields might create faint, detectable distortions around the black hole's shadow, like ripples in a pond revealing the shape of a submerged rock. While we don't yet have telescopes sensitive enough to spot these signatures, next-generation instruments like the Laser Interferometer Space Antenna LISA or advanced radio telescope arrays could one day catch these whispers in the dark. This discovery doesn't just challenge Einstein, it reshapes how we see the universe. If black holes aren't the blank slates we thought, they could be cosmic archivists holding onto secrets we're only beginning to decipher. And as we peer closer, we find yet another way black holes manipulate reality by bending light itself. When a black hole's gravity warps spacetime, it doesn't just trap matter, it twists the very paths of light rays passing nearby. This effect, called gravitational lensing, turns black holes into cosmic magnifying glasses. Imagine staring at a star directly behind a black hole. Instead of vanishing, the star's light bends around the black hole's edges, creating eerie rings or even multiple images of the same star, like a funhouse mirror for the cosmos. The Event Horizon Telescope's iconic image of M87's black hole revealed this very phenomenon, with light swirling around the event horizon like water circling a drain. But lensing isn't just a visual spectacle. By studying how black holes distort background starlight, astronomers can map their gravitational fields with astonishing precision. Some theories even suggest that hairy black holes, those with quantum fields, could produce unique lensing patterns like subtle flares or asymmetries in the light rings. It's as if the universe is leaving us breadcrumbs, hinting at the hidden structures clinging to these dark giants. The more we learn, the clearer it becomes. Black holes aren't the simple, sterile objects we once imagined. They're dynamic, complex, and maybe even a little messy, with hair ruffled by quantum winds and gravity that paints the sky with stolen starlight. And if we're lucky, the next breakthrough will let us comb through those strands, revealing secrets woven into the very fabric of spacetime. Einstein's theory of relativity didn't just predict black holes, it revealed they could be the universe's ultimate illusionists, bending light like cosmic magicians. This eerie phenomenon, called gravitational lensing, turns black holes into nature's telescopes, warping the fabric of spacetime so severely that light from distant stars and galaxies twists around them like a funhouse mirror. The result, multiple ghostly images of the same object, stretched into glowing rings known as Einstein rings, named after the physicist who first dreamed them up. Take the Event Horizon Telescope's groundbreaking image of the supermassive black hole in galaxy M87, that fiery donut of light circling the darkness. That's lensing in action. The black hole's gravity is so intense that photons, particles of light orbiting just outside the event horizon, get bent into a perfect circle, creating a halo of warped starlight. But sometimes the effect is even stranger. If a star or galaxy sits directly behind a black hole from our viewpoint, its light can split into multiple images like a celestial mirage. Imagine holding a wine glass up to a candle. The curved glass distorts the flame into several flickering copies. A black hole does the same thing, but with space-time itself as the lens. This isn't just a visual marvel, it's a scientific goldmine. By studying these distorted images, astronomers can map a black hole's gravitational field with precision, weighing it more accurately than any scale. The shape of an Einstein ring can even reveal how fast the black hole spins, as rotation twists spacetime like a whirlpool, leaving subtle fingerprints in the light's path. Some theories suggest that hairy black holes, those with quantum fields clinging to their horizons, might produce asymmetrical rings, offering clues to the hidden structures lurking just beyond the event horizon. But the real hunt is for something even more elusive: naked black holes. Most black holes are shrouded in accretion disks or cloaked by dust, but a hypothetical naked black hole would be stripped bare, visible only through its lensing effects on background stars. Spotting one would be like finding a ghost: no glowing gas, no telltale X-rays, just the telltale warping of light betraying its presence. If they exist, these invisible giants could be hiding in plain sight, their gravity acting as cosmic magnifying glasses for objects billions of light-years behind them. Gravitational lensing doesn't just show us black holes, it lets us see through them, using their monstrous gravity as a lens to peer deeper into the universe than any telescope could alone. And in that warped starlight, we might just find answers to questions we haven't even thought to ask yet. What if a black hole's singularity wasn't hidden behind an event horizon at all? Imagine a cosmic monster stripped bare, a naked singularity, where the infinitely dense core of a black hole lies exposed to the universe. No cloak of darkness, no point of no return, just raw gravitational chaos visible for all to see. This idea isn't just wild speculation. It's a direct challenge to one of astrophysics' deepest assumptions: cosmic censorship, the notion that nature always hides singularities behind event horizons to preserve the orderly fabric of spacetime. But if naked singularities exist, they'd tear that assumption apart, revealing the universe's ugliest secrets without a shred of modesty. The concept was first proposed by mathematician Roger Penrose in the 1960s, who argued that singularities must be clothed by event horizons, a cosmic firewall preventing their infinite weirdness from leaking into the wider universe. Violating this rule would mean gravity could run amok, bending spacetime into knots where time stutters, causality shatters, and the predictable laws of physics dissolve into madness. Picture a traffic intersection where cars ignore all lights and signs, colliding in infinite loops. That's the chaos a naked singularity could unleash. Yet mathematics doesn't always obey our preferences. Certain solutions to Einstein's equations, like the spinning Kerr black hole, flirt with nakedness. If a black hole rotates fast enough, its event horizon could shrink to nothing, leaving the singularity exposed like a wound in reality. Some theories even suggest colliding black holes might momentarily bare their singularities during mergers, like cosmic curtains briefly pulled aside. But here's the catch: most physicists believe nature has a failsafe. The same spin that threatens to unmask a singularity would likely trigger instabilities, waves of energy or quantum effects that either slow the rotation or collapse the singularity back behind a horizon. It's as if the universe has a self-correcting code, patching its own glitches before they corrupt the system. But let's say a naked singularity did form. What then? For starters, it wouldn't behave like a typical black hole. With no event horizon, light and matter could escape its gravitational grip, though not unscathed. Anything approaching would still be shredded by tidal forces, but the debris might be flung back into space, twisted into bizarre forms by the singularity's infinite gravity. Astronomers could, in theory, observe the singularity directly, watching as it warps background starlight into grotesque, ever-shifting shapes. Some models even suggest naked singularities could emit unpredictable bursts of energy, like cosmic fireworks sparked by space-time itself unraveling. The taboo around these objects isn't just about preserving mathematical elegance, it's about survival. A naked singularity could be a factory for paradoxes, where time loops allow information to escape black holes unscrambled or where effects precede causes. Imagine tossing a book into one and getting back a pristine copy before you even threw it. Such violations of causality would make the universe fundamentally unpredictable, a place where the past isn't fixed and the future isn't bound by logic. Yet for all their dangers, naked singularities might hold the key to black holes' ultimate fate. If Hawking radiation slowly evaporates a black hole, what happens when the horizon shrinks to nothing? Does the singularity vanish in a puff of quantum uncertainty, or does it stand exposed in its final moments, blinking out of existence like a dying ember? Some theories suggest the latter, offering a fleeting glimpse of the universe's most forbidden spectacle before it winks out forever. The hunt for these cosmic rule breakers isn't just academic, it's a test of whether the universe plays fair. If we ever found one, it wouldn't just rewrite physics, it would force us to confront a reality where the most terrifying monsters aren't hidden in the dark but staring right back at us. Stephen Hawking's most unsettling prediction wasn't that black holes glow, it's that they can vanish, not with a bang but with a whimper. Over trillions upon trillions of years, Hawking radiation siphons away a black hole's mass, particle by particle, until the unthinkable happens: the cosmic titan shrinks to nothing. But here's the twist: when a black hole nears the end of its life, the rules get blurry. Does it wink out of existence entirely, leaving behind empty space? Or does some bizarre remnant linger, a fossilized knot of quantum information, a speck of space-time so dense it defies logic? Picture a black hole the size of a mountain evaporating down to the mass of an asteroid, then a boulder, then a grain of sand. As it shrinks, Hawking radiation intensifies, transforming from a faint whisper into a screaming torrent. In its final seconds, the dying black hole could unleash energy equivalent to millions of hydrogen bombs, a flash brighter than a supernova, visible across the cosmos. But then silence, or is there? Some theories suggest that quantum gravity prevents total evaporation, leaving behind a microscopic relic, a Planck star, or quantum bounce, where the singularity rebounds like a compressed spring. Others argue that spacetime itself might snap like a rubber band, sealing the black hole's fate with no trace left behind. The real enigma isn't the energy, it's the information. Quantum mechanics insists that information can never be destroyed, only scrambled. But if a black hole evaporates completely, where does all the data about swallowed stars, planets, and particles go? One camp believes Hawking radiation carries hidden imprints, like cosmic Morse code preserving the black hole's history in subtle particle patterns. Another proposes that information escapes into a baby universe, birthing a new cosmos inside the dying black hole's corpse. The most radical idea, that the information was never truly inside the black hole at all, but plastered across its event horizon like a holographic sticker, waiting to peel away as radiation. This isn't just theoretical chess. The fate of evaporating black holes could reveal whether space-time is fundamentally pixelated, whether parallel universes exist, or if reality itself has a built-in delete button. And while we'll never witness a black hole's death, the universe isn't old enough yet. The equations hint that their final moments might be the ultimate cosmic magic trick, disappearing while leaving the audience wondering if the act was ever real at all. If black holes are cosmic vacuum cleaners, endlessly sucking matter into oblivion, then white holes are their theoretical opposites, cosmic fire hoses, violently spewing everything out. These hypothetical objects appear in Einstein's equations as the time-reversed twins of black holes, where nothing can enter, only escape. Picture hitting rewind on a black hole's life. Instead of collapsing inward, a white hole explodes outward, ejecting all the matter and energy its counterpart once swallowed. It's as if the universe has a cosmic undo button, and white holes are the result. The math allows for their existence, but do they exist in reality? Loop quantum gravity, a leading theory attempting to unite relativity and quantum mechanics, suggests they might. When this framework models black hole collapse, it predicts that the crushing gravity at the singularity could rebound, turning the black hole inside out and birthing a white hole. Think of it like squeezing a rubber ball until it pops back with a burst of energy, except here, the rubber ball is space-time itself. Some even speculate that the Big Bang could have been a white hole event, the explosive birth of our universe from a singularity in some parent cosmos. But here's the catch: white holes would be spectacularly unstable. Unlike black holes, which grow by devouring matter, white holes would shrink as they expel it, their energy draining until they vanish in a final burst. And because nothing can fall in, they'd have no way to replenish themselves. That raises a tantalizing question: could one suddenly appear in our universe today? Theoretically, if an ancient black hole finally finished its quantum bounce, we might witness a white hole flaring into existence, ejecting decades, or even centuries of trapped material in seconds. Some have even speculated that certain high-energy cosmic explosions, like gamma-ray bursts, could be white holes announcing their brief, violent existence. Now imagine two black holes locked in a death spiral. As they merge, their singularities might not just collide, they could rebound into a white hole, transforming the final moment of their merger from a silent collapse into a brilliant eruption. Gravitational wave detectors like LIGO haven't spotted such an event yet, but the possibility lingers in the equations, waiting for the right cosmic collision to prove it real. Whether white holes are out there or not, they force us to ask, is the universe's most destructive force also its most creative? And if so, what else might be hiding in the equations, just waiting to be discovered? Two black holes locked in a cosmic death spiral are nature's most violent ballet, a dance where the dancers consume each other, shaking the very fabric of space-time with every rotation. As they inch closer, their immense gravity whips surrounding space into a frenzy, sending ripples outward at light speed, gravitational waves that stretch and squeeze everything in their path. These waves aren't just faint whispers, they're the thunderous footsteps of giants, carrying energy equivalent to entire stars being vaporized in an instant. And when the black holes finally collide, the impact doesn't just merge them, it sends a shockwave through space-time itself, a phenomenon scientists call the ring down, where the newly formed black hole wobbles like a struck bell before settling into silence. The details of this merger are where things get truly bizarre. In those final milliseconds, the black hole's event horizons stretch, twist, and finally snap together like cosmic taffy, releasing a burst of energy so powerful it briefly outshines every star in the observable universe combined. Simulations reveal that the merged black hole doesn't just sit quietly, it vibrates at specific frequencies, shedding distortions in a process akin to a drop of water smoothing out after a splash. These vibrations, or quasi-normal modes, are the black hole's way of settling into its new shape, and they carry fingerprints of its mass, spin, and even the wild physics that govern the collision. But the real mystery lies in whether these cataclysmic events hide secrets beyond Einstein's relativity. During the merger's peak chaos, the curvature of spacetime becomes so extreme that quantum effects might briefly take over, revealing glimpses of a deeper theory of gravity. Some physicists speculate that microscopic quantum hairs could flicker into existence in these moments, tiny structures encoding information about the black hole's pre-merger states. Others wonder if the ring-down could show subtle deviations from Einstein's predictions, hinting at hidden dimensions or exotic matter at play. The LIGO and Virgo observatories have already caught dozens of these mergers, each chirp in their gravitational wave data telling a story of how black holes tango in the dark. But the most tantalizing signals might still be hiding in the noise, mergers so extreme they bend the rules, or so ancient they echo from the universe's youth. Every collision is a laboratory for the most extreme physics imaginable, and with each new detection, we're not just listening to the universe's symphony, we're decoding the sheet music of reality itself. What if black holes aren't just cosmic vacuum cleaners but ticking time bombs capable of rewriting the very laws of physics in an instant? This nightmare scenario, known as false vacuum decay, hinges on one terrifying possibility. The Higgs field, the invisible quantum molasses that gives particles mass, might not be in its lowest energy state. Like a marble resting precariously on a hill, it could be stable for now, but one nudge away from rolling into a deeper valley, rewriting reality as it goes. And the ultimate nudges might come from black holes, whose extreme gravity could trigger a catastrophic phase transition, an expanding bubble of death where the laws of physics inside are unrecognizable. Picture this bubble as a cosmic wildfire expanding at light speed. One moment, space behaves as usual. The next, fundamental constants like the speed of light or the strength of electromagnetism shift unpredictably. Atoms unravel, stars blink out, and spacetime itself reconfigures into something alien. The terrifying part, we wouldn't see it coming. The bubble's boundary would move faster than light, giving no warning before it annihilates everything in its path. And black holes, with their unimaginable gravitational energy, could be the matches that ignite this inferno. Some theories suggest their singularities might act like quantum lighters, concentrating enough energy to knock the Higgs field into that lower state, birthing a bubble that consumes the universe from the inside out. But here's where it gets stranger. If black holes can spawn these apocalyptic bubbles, could they also be gateways to something new? The same instability that threatens annihilation might also open tunnels to alternate physics. Imagine the bubble's interior not as a wasteland, but as a newborn universe with its own rules, a cosmic reset button pressed by the black hole's death throes. This idea, championed by physicists like Lee Smolin, suggests black holes might be cosmic reproductive organs, birthing new universes where the fundamental constants are slightly tweaked. In this wild scenario, our own universe could be the offspring of a black hole in some parent cosmos, its laws of physics shaped by the chaotic conditions of that collapse. The Higgs field's instability remains unproven, and the odds of a black hole triggering vacuum decay are vanishingly slim. But the sheer possibility forces us to confront a profound truth. Black holes aren't just objects in space. They're potential architects of reality, capable of both destruction and creation on scales we can barely fathom. Whether as harbingers of cosmic doom or midwives of new universes, they remind us that the universe's deepest secrets might be hiding in the abyss, waiting for the right conditions to rewrite everything. What if the spooky connection between entangled particles wasn't just a quantum quirk, but a microscopic wormhole hiding in plain sight? This mind-bending idea, known as ER=EPR, suggests that entanglement, the phenomenon Einstein famously called spooky action at a distance, might actually be particles linked by tiny bridges through spacetime. The theory stitches together two seemingly unrelated concepts: Einstein-Rosen bridges, hypothetical wormholes, and Einstein-Podolsky-Rosen entanglement, quantum-linked particles. The implications are staggering. Every time particles become entangled, they might be forging invisible tunnels through the fabric of reality itself. Let's break it down. Imagine two electrons entangled so that measuring one instantly determines the state of the other, no matter how far apart they are. Under ER=EPR, that instantaneous connection isn't magic, it's geometry. A microscopic wormhole, too tiny to traverse but real, could thread between them, creating a shortcut through spacetime that explains their eerie synchronicity. It's as if the universe cheats by folding space, making spooky action just physics in disguise. This idea doesn't just demystify entanglement, it could revolutionize our understanding of black holes. If entangled particles are secretly connected by wormholes, could the same be true for black holes? Some physicists speculate that when two black holes are entangled, they might share a wormhole to a theoretical structure called a traversable wormhole that could, in principle, allow matter to pass through. Picture two black holes in distant galaxies, their singularities linked by a tunnel where gravity flips inside out, turning the inescapable pull of one into the explosive push of the other. The ER=EPR conjecture also offers a tantalizing clue to the black hole information paradox. If information swallowed by a black hole isn't lost but encoded in Hawking radiation, perhaps it's transmitted through these quantum wormholes, preserving the universe's data like a cosmic backup drive. String theorists have even modeled this, showing how wormholes could act as holographic channels, shuttling information between the black hole's interior and its entangled radiation outside. But here's the twist: these wormholes aren't the cosmic subway rides of sci-fi. They're fleeting, unstable, and vanishingly small, more like quantum stitches in spacetime than usable tunnels. And yet, their mere possibility blurs the line between quantum mechanics and gravity, two theories that have resisted unification for a century. If ER=EPR holds up, it could mean that spacetime itself is woven from entanglement, with every quantum connection subtly warping the geometry of the universe. The most radical implication: black holes might not be isolated monsters but nodes in a vast, hidden network entangled across cosmic distances, their singularities threaded together by spacetime's invisible seams. If true, the universe's darkest objects could also be its most connected, whispering secrets through wormholes we're only beginning to imagine. Black holes might not be the bald, featureless objects we once thought. Recent breakthroughs suggest they could have a kind of quantum hair, a delicate fuzz of low-energy particles clinging to their event horizons like cosmic static. These aren't literal strands, but subtle imprints left by particles called soft photons and gravitons, which carry barely any energy yet might hold the key to solving one of physics' biggest headaches, the black hole information paradox. Here's the twist: when matter falls into a black hole, it doesn't just vanish without a trace. According to quantum field theory, its presence slightly distorts the surrounding space-time, leaving behind faint ripples in the form of these soft particles. Think of it like dragging your hand through a foggy mirror. The glass clears for a moment, leaving behind a smudged pattern. Similarly, as stars or gas clouds plunge past the event horizon, they excite these low-energy particles, creating a quantum memory etched into the black hole's boundary. This soft hair isn't just random noise, it's a meticulous record of everything the black hole has ever consumed. The math behind this is staggeringly elegant. In 2016, physicists Stephen Hawking, Malcolm Perry, and Andrew Strominger showed that these soft particles could carry conserved charges, quantum fingerprints that preserve information without violating any known laws. Their equations revealed that even the gentlest photons or gravitons, with wavelengths stretching across the entire universe, could encode details about incoming matter's energy, momentum, and even quantum states. It's as if the event horizon is a vast, ultra-high-resolution hard drive, with each soft particle acting like a pixel in a cosmic hologram. But how does this solve the information paradox? If soft hair exists, then Hawking radiation, the faint glow black holes emit, might not be thermal noise after all. Instead, it could be subtly imprinted with data from these soft particles, like a radio signal encrypted with hidden messages. As the black hole evaporates, this information wouldn't vanish. It would leak out, scrambled but intact, in the radiation itself. Recent simulations even suggest that the chaotic dance of soft photons at the horizon could generate a kind of holographic noise, a quantum jitter that preserves the universe's ledger without needing firewalls or fuzzballs. The implications are cosmic. If black holes truly have quantum hair, then spacetime itself might be far more malleable than we imagined, capable of storing information in its very fabric. It's a revelation that blurs the line between gravity and quantum mechanics, suggesting that the event horizon isn't just a boundary, it's a dynamic, living surface where the universe keeps its receipts. And if we can decode the whispers of these soft particles, we might finally answer the haunting question: where does information go when it falls into the abyss? The answer could be hiding in the faintest fuzz of all. What if the smooth, continuous space around a black hole isn't so smooth after all? Imagine zooming in on the event horizon with a microscope so powerful it reveals spacetime not as a flawless fabric, but as a shimmering, pixelated static, like a cosmic television screen tuned between channels. This is the mind-bending concept of holographic noise, the idea that at the smallest scales, spacetime itself might be fractured into discrete, vibrating bits. Near a black hole where gravity warps reality to its limits, this quantum fuzz could become visible, transforming the boundary between the known and the unknown into a buzzing, digital haze. This isn't just wild speculation. The holographic principle, born from black hole thermodynamics, suggests that all the information inside a black hole's volume might be encoded on its two-dimensional surface like a 3D movie projected from a flat screen. If true, then spacetime near the horizon could resemble a vast, ultra-fine grid, with each pixel representing a fundamental unit of reality. These pixels wouldn't be silent, they'd thrum with quantum fluctuations, creating a background hum of holographic noise. Some theorists argue this noise could even be detectable, like the faint hiss of a radio picking up distant signals. Future gravitational wave detectors, like the planned Laser Interferometer Space Antenna LISA, might be sensitive enough to eavesdrop on this static. Just as microphones capture sound waves, LISA ultra-precise instruments could measure spacetime's quantum jitter, revealing whether the universe has a hidden resolution limit. If the noise matches predictions, it would be the first direct evidence that spacetime is pixelated, a landmark discovery proving that gravity and quantum mechanics merge at the smallest scales. But here's the wildest twist. If spacetime is computational at its core, could black holes be nature's quantum computers? The holographic principle hints that the event horizon isn't just a boundary, it's a processor, performing calculations as particles fall in and information gets scrambled. Each pixel of holographic noise might represent a logic gate in a cosmic circuit, with the black hole's evolution mirroring an unfathomably complex algorithm. Some scientists, like MIT's Seth Lloyd, have even speculated that the universe itself could be a simulation running on black hole hardware, with every gravitational interaction a step in the computation. Whether or not black holes are crunching numbers, the search for holographic noise is more than a fringe pursuit. It's a direct test of whether spacetime is continuous or discrete, whether information truly lives on the surface of things, and whether the universe's deepest truths are written in static. The answers might not just redefine black holes, they could reveal the very code of reality. What if the most powerful computers in the universe weren't built by civilizations, but by gravity itself? Black holes, with their mind-bending physics, might be nature's ultimate processors, capable of calculations so complex they dwarf anything silicon-based AI could achieve. The concept isn't science fiction. Visionaries like physicist Freeman Dyson speculated that advanced civilizations could harness black holes as black hole brains, turning these cosmic monsters into unimaginably powerful quantum computers. Think of a black hole's event horizon not as a boundary, but as a cosmic hard drive. Every bit of information that falls in gets scrambled and smeared across its surface, thanks to the holographic principle. This means the horizon could act like a quantum circuit board, with each infinitesimal patch representing a computational operation. The more massive the black hole, the more qubits it could theoretically hold, with a single stellar mass black hole potentially storing more information than all the data ever created by humanity. Some calculations suggest a black hole the size of our Sun could perform 10 to the power of 80 operations per second, a number so vast it exceeds the total number of atoms in the observable universe. But how would an advanced civilization actually use this? Dyson's black hole brain idea involves surrounding a small, artificial black hole with a Dyson sphere, a megastructure capturing its Hawking radiation. Instead of letting the energy escape as waste heat, they could encode data into the radiation patterns, using the black hole's natural evaporation as a computational process. It's like programming a cosmic alarm clock where each tick isn't just a moment in time, but a step in a universe-scale calculation. The black hole's extreme gravity would also slow time near its surface, allowing for ultra-fast processing relative to the outside world, a built-in time dilation supercharger. For us, harnessing this power is still the stuff of dreams, but the physics doesn't forbid it. Imagine a future where we create micro black holes in particle accelerators, stabilizing them with precise magnetic fields or cosmic strings. These tiny singularities, smaller than an atom but heavier than a mountain, could become the cores of quantum supercomputers, solving problems like climate modeling or drug discovery in picoseconds. Of course, the risks are as colossal as the rewards. One miscalculation, and your computer becomes a doomsday device. Yet the most tantalizing possibility isn't just computation, it's communication. If black holes can preserve information in their Hawking radiation, they might also transmit it across space or even time. An advanced civilization could use merged black holes as entangled nodes in a galactic internet, sending messages through wormholes or encoding data in the ringing of spacetime after collisions. The universe might already be buzzing with such networks. Hidden in plain sight, their signals disguised as gravitational waves or cosmic static. Black holes challenge us to rethink not just physics, but the limits of intelligence itself. If nature can build a processor where space-time itself is the circuitry, then the cosmos might be far stranger and far smarter than we ever imagined. And somewhere in their dark hearts, the answers to the universe's greatest mysteries could already be computed, waiting for us to decipher them. Black holes aren't just cosmic destroyers, they're the universe's ultimate power plants, hiding energy reserves that dwarf anything we could harvest from stars. Picture a spinning black hole, its rotation twisting space-time into a vortex of pure gravitational force. This isn't just a spectacle, it's a battery waiting to be tapped. In the 1960s, physicist Roger Penrose revealed how to steal energy from these cosmic whirlpools using a mind-bending trick now called the Penrose process. Here's how it works. If you fire a particle into the black hole's ergosphere, the region just outside the event horizon where spacetime itself is dragged into rotation, the particle can split in two. One fragment plunges into the abyss, but the other gets slingshot outward with more energy than it started with. The black hole pays the bill, losing a fraction of its spin to fuel the escapee. It's like dropping a coin into a spinning roulette wheel and getting two back, a gravitational casino where the house always loses. But the real jackpot comes from superradiance, a quantum phenomenon where waves like light or even gravitational waves bounce off a spinning black hole's ergosphere with amplified energy. Imagine shouting into a tornado and having your voice echo back louder. Under the right conditions, the black hole's rotation pumps energy into incoming waves, creating a feedback loop that could, in theory, be harvested. Freeman Dyson, the visionary physicist behind Dyson spheres, speculated that advanced civilizations might build black hole generators, surrounding these cosmic engines with mirrors or superconducting nets to trap and extract the amplified radiation. A single stellar mass black hole could provide the energy output of 1 trillion suns, enough to power a galaxy-spanning civilization. The catch, engineering on a scale we can barely fathom. To harness a black hole's spin, you'd need infrastructure orbiting at relativistic speeds, withstanding tidal forces that shred ordinary matter. Yet the rewards could redefine cosmology. If civilizations across the universe are already doing this, the telltale signatures, like anomalous energy emissions or artificial structures near black holes, might be hiding in our telescope's data. Some theorists even suggest that quasars, those universe-brightening behemoths, could be natural superradiance engines, their dazzling light fueled by the relentless spin of their central black holes. Black hole energy isn't just sci-fi, it's a reminder that the universe's most destructive forces might also be its most generous. And if we ever crack the code to tap them, we won't just be solving an energy crisis. We'll be stepping into the league of cosmic engineers, turning the darkest objects in existence into beacons of limitless power. Primordial black holes might be hiding in the most unexpected place, the invisible glue holding galaxies together. For decades, astronomers have known that dark matter, the mysterious substance making up 85% of the universe's mass, can't be ordinary particles. But what if it's not particles at all? What if it's an invisible sea of ancient black holes forged in the universe's first chaotic moments? This idea isn't new, but recent discoveries have narrowed the hunt and revealed why some primordial black holes can't be the dark matter we're searching for. Start with the smallest ones. Black holes lighter than an asteroid would have evaporated by now due to Hawking radiation, their lives ending in a flash of gamma rays long before the modern cosmos took shape. That rules out anything below 1 billion metric tons, no tiny, planet-sized black holes lurking unseen. On the other hand, primordial black holes larger than 100 solar masses would leave scars we'd notice. Their gravity would bend background starlight as they pass through galaxies, creating telltale microlensing events that telescopes like Hubble and Subaru have failed to find in sufficient numbers. But here's where the plot thickens. There's a tantalizing window where primordial black holes could still be hiding, between the mass of a large asteroid and a small moon. These Goldilocks black holes would be too heavy to evaporate, yet too light to distort light noticeably. They'd drift through galaxies like invisible icebergs, their collective gravity tugging on stars just enough to explain dark matter's effects. Some theories even suggest these mid-sized relics could be the seeds of supermassive black holes, growing over billions of years by swallowing gas and merging with one another. Yet there's a glaring problem. The universe might have made too many of them. If primordial black holes in this range were abundant enough to account for all dark matter, they'd also have triggered other observable effects, like disrupting the delicate patterns of the cosmic microwave background or leaving gaps in the oldest star clusters. So far, those fingerprints are missing. It's as if the universe is teasing us with a solution that fits some clues but breaks others. The real twist. Primordial black holes might still be part of the dark matter puzzle, just not the whole answer. A mix of these ancient relics and other exotic particles could explain why some galaxies seem to have more dark matter than others, or why certain cosmic structures formed faster than expected. The hunt isn't over. New telescopes like the Vera Rubin Observatory will scan the skies for the faint flickers of hidden black holes, while gravitational wave detectors listen for the whispers of long-ago collisions. If even a fraction of dark matter turns out to be primordial black holes, it would rewrite cosmic history. These time capsules from the Big Bang wouldn't just solve a mystery, they'd reveal a universe far stranger than we imagined, where the darkest objects in existence are also the oldest. And that raises an even bigger question. What else is hiding in the shadows at the dawn of the cosmos when the universe was barely a toddler? Something impossible already existed, supermassive black holes weighing billions of suns. These cosmic behemoths, like the one powering the quasar Euler's J1342 plus 0928, were fully grown just 690 million years after the Big Bang. That's like finding a skyscraper in the middle of a prehistoric jungle, an anomaly that defies everything we know about cosmic evolution. Normally, black holes grow by slowly feasting on gas and merging with others over billions of years. But these ancient monsters didn't have time for that. They were born big, the question keeping astrophysicists up at night. How? One radical answer lies in the direct collapse theory. Imagine a primordial cloud of pure hydrogen. No stars, no galaxies, just vast reservoirs of gas left over from the Big Bang. Under the right conditions, these clouds could have skipped the star-forming stage entirely, collapsing directly into black holes thousands of times more massive than our Sun. It's like a cosmic cheat code. Instead of a star burning for millions of years before collapsing, the whole cloud implodes at once, birthing a ready-made giant. These seed black holes, feasting on the dense gas of the early universe, could have ballooned into supermassive status in record time. But here's the twist: some theories suggest these black holes didn't just grow fast, they might be older than galaxies themselves. In this scenario, supermassive black holes formed first, their gravity sculpting the swirling gas around them into the first protogalaxies. It's a complete flip of the traditional story where galaxies birth black holes at their centers. Instead, the black holes may have been the architects, their immense pull gathering the raw materials to build their cosmic homes. observations of distant quasars shining with the brightness of 1 trillion suns support this idea. Their host galaxies often appear oddly underdeveloped, as if the black hole outgrew its surroundings. The implications are staggering. If supermassive black holes came first, they didn't just shape galaxies, they dictated the universe's structure. Their gravity could have triggered the formation of the first stars. Their radiation ionized the cosmic fog of the early universe, and their mergers might have seeded the web of dark matter we see today. The James Webb Space Telescope is now peering into this ancient era, hunting for baby supermassive black holes in their cribs. Every new detection brings us closer to answering the ultimate question: did black holes build the cosmos, or did the cosmos build them? The answer might rewrite the story of how everything came to be. Long before the first stars flickered to life, the universe might have been lit by something far stranger: dark stars. These hypothetical monsters wouldn't burn like our sun, fueled by nuclear fusion. Instead, they'd glow with the eerie heat of annihilating dark matter, particles colliding and releasing energy at their cores. Imagine a celestial furnace where the fire isn't made of atoms, but of the invisible stuff that binds galaxies together. These dark stars could have grown to staggering sizes, millions of times more massive than our sun, before collapsing into the supermassive black holes that now lurk in galactic centers. The math behind them is both elegant and unsettling. In the early universe, vast clouds of hydrogen and dark matter might have clumped together under gravity. Normally, such a cloud would ignite fusion, becoming a star. But if dark matter was dense enough, its self-annihilation could have provided an alternative power source, heating the gas from within and preventing collapse. The result, a bloated, quasi-stable behemoth, radiating not with starlight, but with the soft glow of particle destruction. These dark stars would have been colder than fusion-powered stars, but far larger, stretching across solar systems, their surfaces barely hotter than a summer's day. Yet their true legacy lies in their fate. Once the dark matter fuel ran out, these giants would have imploded directly into black holes, skipping the supernova stage entirely. This could explain how supermassive black holes appeared so early in cosmic history. They weren't built slowly by mergers, they were born ready-made from the corpses of their dark predecessors. Some theories even suggest that dark stars could still exist today in regions rich with dark matter, lurking unseen in the voids between galaxies. But not all black holes stay put. Some go rogue, ejected from their galaxies by violent collisions or gravitational slingshots. These lone wanderers drift through intergalactic space, invisible except for the occasional flicker of light as they rip apart a stray star or warp the light of distant quasars. Astronomers have already spotted a handful of these nomads, their presence betrayed by the distorted glow of background stars bending around their invisible mass. One rogue black hole detected in 2022 weighs 7 times our sun's mass and drifts alone 5,000 light-years away, a cosmic ghost with no home. The universe's darkest objects might not just be in points of stellar life. They could be the remnants of a primordial era when dark matter ruled, and the first light came from the annihilation of the unseen. Whether as ancient seeds or modern drifters, black holes continue to rewrite the story of the cosmos, one mystery at a time. Some black holes don't stay put, they go rogue. Hurtling through the cosmos at millions of miles per hour, these lone wanderers are the galactic equivalent of drifters, untethered from the galaxies that birthed them. Their origin story begins with violence. When two galaxies collide, their central supermassive black holes spiral toward each other in a gravitational dance, eventually merging with a cataclysmic burst of gravitational waves. But sometimes the recoil from that collision is so powerful it flings the newly formed black hole clear out of its galaxy. sending it careening into the void like a cosmic billiard ball. These rogue black holes are invisible ghosts, betraying their presence only through subtle gravitational tricks. Without an accretion disk to glow with superheated gas or a cluster of stars to light their way, they drift undetected until something crosses their path. A star straying too close might be torn apart in a tidal disruption event, flaring briefly as it's shredded into a stream of luminous debris, or background starlight might warp around the black hole's immense gravity, a phenomenon called microlensing that creates fleeting, distorted copies of distant stars. In 2022, astronomers spotted one such gnome at roughly 5,000 light-years away, its 7 solar mass presence revealed only by the way it bent the light of a star behind it, a telltale flicker in the darkness. But here's the unsettling question. What if one passed through our solar system? The odds are astronomically low, but the consequences would be staggering. Even a small stellar mass black hole, just a few times heavier than our Sun, would wreak havoc long before it arrived. Its gravity would perturb the orbits of planets, tugging them like invisible puppet strings. Neptune might drift out of place first, followed by Uranus' subtle anomalies that would baffle astronomers until the truth became undeniable. As the black hole neared the inner solar system, its tidal forces would stretch and compress Earth, triggering earthquakes, volcanic eruptions, and tsunamis on an apocalyptic scale. The night sky would twist into surreal patterns as starlight bent around the intruder, and our planet's orbit, if it survived at all, could be flung into a frozen exile or a fiery plunge toward the sun. Yet the most chilling detail, we might not see it coming. Unlike asteroids or comets, a rogue black hole emits no light, no radiation, just the faintest whisper of gravity. By the time its effects became undeniable, it could already be too late. Thankfully, the cosmic void is vast, and the chances of such an encounter are vanishingly slim. But the existence of these nomads reminds us that the universe is anything but static. Black holes aren't just lurking in galactic centers, they are on the move, silent and unstoppable, rewriting the rules of gravity wherever they roam. And somewhere in the darkness between galaxies, another one might be drifting, unseen, on a path we'll never predict. Imagine a planet orbiting just far enough from a black hole to avoid spaghettification, but close enough to bask in the eerie glow of Hawking radiation. While this sounds like the setting for a sci-fi nightmare, it might also be the ultimate cradle for life unlike anything we've ever known. The extreme environment near a black hole defies all Earth-based logic, yet nature has a habit of thriving in places we once thought impossible. From bacteria living in nuclear reactors to microbes flourishing in boiling hydrothermal vents, extremophiles on Earth prove life adapts to the harshest conditions. Could the same resilience exist near the universe's most destructive force? The key lies in energy. On Earth, life harnesses sunlight or chemical reactions, but near a black hole, tidal forces and Hawking radiation could replace photosynthesis. Picture a world stretched and compressed by its host black hole's gravity, its crust constantly kneaded like dough. This friction might generate geothermal heat, creating subsurface oceans akin to Jupiter's moon Europa. Meanwhile, Hawking radiation, though faint, could provide just enough warmth to sustain chemical reactions in the atmosphere or shallow seas. Organisms might evolve to metabolize this exotic energy, treating the black hole's quantum glow like a cosmic sun. Some theories even suggest that charged particles swirling in the black hole's magnetosphere could spark prebiotic chemistry, assembling complex molecules in the turbulence. The real wild card, time dilation. A planet close to the event horizon would experience time so slowly that billions of years pass elsewhere in the universe between its sunrises. Evolution here would operate on an unimaginable scale. Organisms might have near eternity to adapt, their biology refined over epochs that dwarf Earth's entire history. Alternatively, life might arise fleetingly in the brief windows between cataclysmic tidal shifts, blooming like desert flowers after rain before being wiped clean by the next gravitational tremor. But the most tantalizing idea isn't just life surviving near black holes, it's black holes creating life. The same chaotic particle collisions that power Hawking radiation could also forge organic molecules, scattering them into surrounding space. Some models suggest that the jets of supermassive black holes might carry prebiotic materials across galaxies, seeding star systems with the raw ingredients for life. In this view, black holes wouldn't just be destroyers, they'd be cosmic gardeners, cultivating complexity in the unlikeliest of soils. Whether such life exists remains speculative, but the possibility reshapes how we see the universe's darkest corners. If biology can emerge in the shadow of a black hole, then life might not be a rare fluke but a fundamental feature of reality, blooming wherever energy and persistence intersect. And that raises a haunting question. If life can cling to the edge of oblivion, where else might it be hiding? What if every black hole is a cosmic Matryoshka doll, hiding an entire universe inside its singularity? This radical idea, championed by physicist Lee Smolin, flips our understanding of reality on its head, suggesting that black holes aren't endpoints but beginnings. In this mind-bending view, the crushing collapse of a singularity might not be the end of space-time, but the spark of a new one. Picture a dying star's core imploding beyond the event horizon, not into infinite density, but into a rebound, a big bang in miniature, birthing a fresh cosmos with its own laws of physics. Our universe, in this scenario, could be the offspring of a black hole from some parent reality, and the black holes dotting our own skies might themselves be pregnant with universes yet unborn. This isn't just poetic speculation. Smolin's theory of cosmological natural selection proposes an evolutionary mechanism for universes. Just as biological mutations drive diversity in life, each black hole-born universe could inherit slightly tweaked physical constants like the strength of gravity or the mass of electrons. Universes that produce more black holes would reproduce more often, leading to a multiverse where the laws of physics favor black hole formation. It's Darwinism scaled up to cosmic proportions, with black holes as the reproductive organs of reality itself. The eerie fine-tuning of our universe's constant so perfect for stars, planets, and life might not be luck, but the result of eons of cosmic selection favoring black hole-rich cosmoses. But Smolin's vision isn't the only cyclical model dancing through theoretical physics. Ancient Hindu cosmology spoke of universes breathing in and out in vast cycles of creation and destruction. Modern physics echoes this poetry with the conformal cyclic cosmology of Nobel laureate Roger Penrose, where the distant future of one universe becomes the Big Bang of the next. In Penrose's model, as black holes evaporate and particles lose mass over trillions of years, space-time smooths out until it's indistinguishable from the featureless void before the Big Bang, a cosmic reset button. The ghostly imprints of long-dead black holes, called Hawking points, might even linger as faint rings in the cosmic microwave background, like scars from a previous eon. The most startling parallel between these theories, time itself becomes a hall of mirrors. If black holes birth universes, causality loops back on itself. Our cosmic ancestry might trace back through an infinite regression of black hole universes, each tweaking the rules slightly. It's as if the universe is a self-correcting algorithm, iterating through versions until it stumbles upon the perfect parameters for black hole production. And if that's true, the haunting question isn't just where did we come from, but are we the product of a cosmic evolutionary experiment? Whether these ideas hold or collapse under scrutiny, they reveal a profound shift in how we see black holes. No longer just gravitational graves, they become cosmic wombs, potential bridges between realities, engines of creation hidden behind veils of darkness. And if even a fraction of this is true, then the universe's darkest objects might hold its brightest secret, that endings are just beginnings in disguise. From spaghettification to Hawking radiation, from quantum hair to holographic universes, these 35 phenomena aren't just isolated curiosities, they're pieces of the greatest unsolved puzzle in physics. Each one stretches our understanding of reality, bending the rules of relativity, warping the boundaries of quantum mechanics, and forcing us to question everything we thought we knew about space, time, and existence itself. Black holes aren't merely cosmic oddities. They're laboratories where the universe tests its own laws, revealing glimpses of deeper truths hidden just beyond our reach. Consider the contradictions they embody. They're the simplest objects in the universe, defined by just mass, spin, and charge, yet they may also be the most complex, encoding infinite information on their surfaces. They're perfect destroyers, trapping everything that falls in, yet they might also be creators, birthing new universes or powering civilizations. They warp time until it grinds to a halt, yet they could hold the key to understanding its fundamental nature. Every paradox, every mystery at the edge of a black hole is a clue, pointing toward a grander theory that unites gravity and quantum mechanics, the very large and the unimaginably small. Humanity's quest to unravel these enigmas is more than scientific curiosity. It's a journey to understand our place in the cosmos. From Einstein's equations to the Event Horizon Telescope's first image, each discovery peels back another layer of the universe's secrets. But with every answer come new questions, deeper and more profound. Are black holes gateways? Are we living in a hologram? Is space-time itself an illusion? The beauty lies not just in the answers we might find, but in the act of searching, the relentless human drive to explore the unknown. As Carl Sagan once said, somewhere, something incredible is waiting to be known. That somewhere could be the edge of a black hole, where the fabric of reality frays into quantum uncertainty. That something could be the key to unlocking the universe's deepest mysteries. So stay curious, keep questioning, because the next breakthrough, the next revolution in physics might be hiding in the darkness, just beyond the event horizon, waiting for someone bold enough to reach for it. The universe's greatest stories are still being written, and you're part of the adventure.